I did not succeed. Okay, I will just do it the old-fashioned way.
Okay. So
now it's working, right?
Yeah, it works, but you need to go to the first page.
Yeah, true.
Okay, and maybe you enter full screen mode. So
it's fine.
Yeah.
We cannot see the whole page. I think this is
yes.
yeah.
I should. I'm not using a good. I should.
Here, yeah.
I should just use another PDF view. Yeah, this one. So share.
No, share, yes.
Yes, and the PDF and view full screen mode.
Yes.
Yeah, this is fine. Perfect.
Okay, it's okay. Okay,
so I'm very sorry for the delay.
Okay, it's okay. So okay, welcome everyone. So it's our pleasure to have Omar Mohsen from Münster to talk about inhomogeneous pseudo-differential calculus today. And Omar, it's you.
So thanks a lot for the invitation. And so I will talk about inhomogeneous pseudo-differential calculus. This is joint work with Androuilladakis, Van Erb, and Juncken. And this work started almost a year ago now, and it's almost finished. It should appear on arXiv this week, by the end of this week. I mean, we are finalizing the PDF file. So anyway, so the object of study in my talk will be hypoelliptic differential operators. So let's take a linear differential operator on a manifold without boundary, and we are interested in this equation: du is equal to v. And a classical, very well-known definition in analysis is we say that the differential operator is hypoelliptic if it preserves the singular support. So whenever u and v are distributions on M, and which satisfies this equation, if v is smooth on some open set, then u is also smooth on the same open set. You could also write it as the singular support of du. The singular support of u is subset of the singular support of du, if you want. And of course, the definition doesn't really need much motivation. We want to solve differential equations, and if we know that the differential operator is hypoelliptic, then we only need to search for solutions which are distributions, because then they are automatically smooth. And so we have a much bigger arsenal of tools if we allow distributions instead of just looking at smooth functions. And so this is a very nice property of differential operators, but of course it's not always satisfied. It's very easy to see that, for example, you could take R2 and D to be dx, for example, and of course, and u any distribution in Y. So the question is, when is it satisfied and how to verify that this is the case? I will also say that there are many variants in the literature. So you could potentially ask for analytic hypoellipticity, or you could ask for some spaces called Jeffrey spaces between analytic and smooth functions, which allow for functions with compact support. You could also ask, so this, for example, tells you that if V is smooth, then U is smooth, but it doesn't tell you anything if V is CK, for example, or belongs to HS Sokolov space. So you could put conditions like if V belongs to the S Sokolov space, then U belongs to the HL Sokolov space with some relation between S and N. Okay, so there are many variants of this definition, and I will explain why it's important to know that there are many variants of this definition. I will not be interested in analytic variants, only see infinity. So examples of operators. Well, probably the most well-known example is the Laplace operator on Rn. I just write it on R2, and you could add any first-order differential operator, and it will remain hyperelliptic, and I will explain in a moment why. You could also consider on R2 dx squared plus dy. This is a different family, belongs to a different family of differential operators. You could also consider this differential operator. So dx squared plus x dy squared plus lambda dy. Now the condition is more subtle. This is hyperelliptic if lambda is in the outside this set. Okay. And now here are much more subtle and in some sense bad examples. So those things are hyperelliptic for any lambda, but if you tensor them with R, they don't become hyperelliptic, at least not always. Okay, so this is the example 4 is very different from the first 3 examples. If in any of those 3 examples, the first 3, if I add a new variable and I just add dx squared, that variable, then it will always be hyperelliptic. But this example, that's not the case. And so this is type of, I mean, in some sense, the hyperellipticity of this differential operator can be thought of as an accident. It shouldn't have been hyperelliptic, but it just happens. So there are some definitions which should try to modify, strengthen hyperelliptic definitions to eliminate those strange behaviors. For example, if the manifold is Fredholm, I don't think this operator, if the manifold is compact and you put this operator locally, I don't think this operator will be Fredholm, even though it's hyperelliptic. So there are definitions in the literature to try to improve this condition. The condition that I have in mind is called maximally hyperelliptic. It was defined by Helfer and Norigat, and I won't write the definition. It's quite complicated and technical, but what I want to say is that what I really want to study is maximally hyperelliptic differential
I'm
operator.
a little bit confused about the notation. So shouldn't it be absolute value of x? I mean, because when you write x to the sigma, if x is negative and I take sigma equals 1, I will get something which blows up tremendously.
Yes, of course it should be.
Absolute value of x, yeah.
Yes, or you could just put x
square to the sigma over 2, yeah, sure. Okay.
Yes, yes, of course. In fact, I think that's how analysts write it. They don't use absolute value. They use x squared or sigma over 2.
Yeah, sure.
This result is due to 2 Russian mathematicians who I forgot their names, but it was proved in the 80s, I think, late 80s. Part of it in the late 80s and the other in the late 70s. But those are completely outside the scope of what I will talk about. They are proved with different techniques. Yeah. So how one gets that a differential operator is hyperelliptic? Well, the easiest test, if you want, is using the principal symbol. So the principal symbol is very easy to define. If you have a differential operator of order k, locally it has this form. So, and here, so parts which differentiate with order less than or equal to k, then you define the principal symbol this way. So each time you see a d partial dx, you replace it with I xi k. Okay, and you eliminate all of the terms which have order strictly less than k. So, for example, if you have something like this, the principal symbol is this. I like those type of examples. So you eliminate the lower order term and you just put this. Okay, and it should be remarked that this homogeneous polynomial of degree k. So now the easiest test and the most common example of hyperelliptic operators are what's called elliptic operators. So we say that a differential operator is elliptic if its principal symbol only vanishes when xi is 0. This is for any k and xi. If this is 0, then xi is 0. It should, I mean, it's a homogeneous polynomial, so it always vanishes at 0. So you require that the only vanishing point is xi to be 0. Okay, and of course the Laplace operator, which we saw before, is elliptic, but this second example from before is not. And the theorem is that if D is elliptic, then D is hypoelliptic. Okay, and to prove this theorem, one introduces a pseudo-differential calculus, and it proves that in this pseudo-differential calculus, the operator has what's called a parametric or a pseudo-inverse. So I will explain what do we want out of a pseudo-differential calculus, because the goal of the talk will be to define different pseudo-differential calculi. So it will be useful here to say axiomatize the properties that we want. So the pseudo-differential calculus will be an algebra of operators which act on distributions and which take C-infinity functions to C-infinity functions. And they have the property that there is a principal symbol, and the principal symbol should carry only the information that we want to use to prove hypoellipticity. So in the previous example, the principal symbol removed all of the lower order terms. Here, it might remove other terms, but it should keep what we want to use to prove hypoellipticity. Then there should be an invertibility condition for the symbol, which is hopefully easy to check, as we will see. And we say, I don't know if this is a well-established terminology, but it's a terminology I use. A pseudo-differential operator is elliptic in the calculus if its principal symbol is invertible in that calculus. Okay. And finally, an elliptic differential operator in the calculus admits a parametric. By this we mean it's a pseudo-inverse. So it's a differential. It's a pseudo-differential operator in the calculus, which it's not exactly an inverse. The product. So it's an inverse modulo regularizing operators. Those are operators which have smooth kernel. Those are the best operators in analysis because, I mean, they are the properties. They are the operators with the nicest properties because they have the property that they take any distribution, whatever its regularity, and they make it smooth. Okay. So you can't ask more out of those type of operators. And so it tells you that up to regularizing operators, you actually have an inverse. And using the existence of this inverse, you easily see that the operator has to be hypoelliptic. Because, for example, if du is smooth, then p du is smooth because the pseudo-differential operator preserves smooth function. And so u is smooth up to a smooth function. That means that u is smooth. Okay. So immediately from this formula, you get that the differential operator is hypoelliptic if it does have a parametric in the calculus, of course. Okay. So I will go back to the principal symbol and just explain one way to define the principal symbol. Of course, the principal symbol, there are tens of ways to define it. I will just mention one way, which would be quite useful later on when I do the inhomogeneous pseudo-differential calculus, because there it's uglier to define the principal symbol. It's a very simple remark, but it's useful. So if I have the algebra of differential operators, here I mean the filtered, this is a mistake. I mean, the algebra with the filtration of operators of order k. Of course, this is not. And if I have a point in the manifold, I let Ix to be the ideal of functions which vanish at that point. Then I could consider this algebra. So it's without the Ix, it's just a filtered quotient, and the Ix is like a localization of the point X. And it's very simple exercise to see that this algebra is just polynomial algebra of polynomials in n variables, corresponding to the cotangent vectors. It's actually better to write it as polynomials in the cotangent boundary. That's an invariant way to do it. Anyway, so this is one way to define the principal symbol. I mean, if you start with the differential operator, you just take its class of order k, you take its class here, you go up to with the isomorphism, and you get that you get its principal symbol. Okay. Now, as we have seen, elliptic operators give hypoelliptic operators, but except for the first example, all of the others are not elliptic operators. And so the goal is to construct a pseudo-differential calculus where all of the others are elliptic operators. So Folland and Stein had this idea of defining a principal symbol. They are the ones who started this type of thing. They had the idea of defining a principal symbol which is inhomogeneous. Okay. I mean, so if I go back to the example. So for example, if you go here, this is of order 2, this is of order 2, but this is of order 1. But the reason why this operator is hypoelliptic is contained in the part of order 1. So the principal symbol is useless in determining the hypoellipticity of this operator. So you want something which takes into account things of order 1. But you don't want everything of order 1. You want those which are useful to your question. So the question is, what are the things to throw away? What are the things to keep? Okay. Now, I won't present their setting because their setting was only for contact manifolds, and this was generalized by many people. And the goal of our work is to remove as much as possible of the hypothesis, to generalize. So to generalize such calculus without supposing as much as possible. And so I will just do the setting in our case, okay, which is quite general. So our setting, we choose some fixed number, which we call the depth, and we choose some finite number of vector fields. I don't really need finite, only locally finite suffice, but for all purposes, just choose finite number of vector fields. And to each vector field, we'll choose a number, which we want to be its order. So we will declare, and it should be remarked that because the vector fields are not related to each other, local coordinates are really useless. If those generate the foliation, I could do something and use Frobenius theorem. If they generated a contact manifold structure, I could use Darboux theorem. But in general, there are way too many relations between them to local coordinates are not really the good thing to consider. And in fact, the good local coordinates to consider will be explained later on. They are not subsets of the manifold, as we'll see. Anyway, so we declare that xi to be of order I and any other vector field to be of order n. Okay. Of course, some non-trivial relations will be forced upon us because of this, but let's just keep this for the moment. So out of this, we define a pseudo-differential calculus. Okay.
And I am confused here because when you say any other vector field, I mean, for instance, if I multiply by 2, the order shouldn't change. So, I mean.
Yes, that was the next line. So, I mean, I'm using modules. In this next slide, I will use modules. But of course, you are correct. So if a vector field, I can obtain it using relations out of the xi. So for example, if I multiply it by a smooth function, then it preserves the order. If I can obtain it using Lie brackets, I force an order. But at some point, those relations are finite. So I can exhaust all of them, and then I'm good. I will give the setting in the proper way in the next slide, more proper way if you want. And the point is that if one is given, if one has those vector fields, then one can go back and forth between the two settings. So if I have, if I declare that xi is a vector field of order ni, then I have this relation. So x is a, so if I have x is of order k and y is of order l, and then I take the Lie bracket, that's a vector field. But at the same time, it's the commutator, so it's xy minus yx, and x has order k, y has order l. So this is a differential operator of order k plus l a priori. So the difference has to be also of order k plus l. So for example, the order of xi and xj has to be of order ni plus nj, at least ni plus nj. Maybe there are other relations which force it to be of less order. For example, I could, one of those vector fields could be really the Lie bracket, and I could have forced it to be of order 1, for example. But at least I have this. I also have to have 3 Lie brackets and so on. Okay, but it should be remarked that all of the orders have are bigger than or equal to 1. You can see my cursor, right? No.
Yes, we can see your cursor. Yes.
Okay. Thank you. So since each integer is bigger than or equal to 1, each time you take the Lie bracket, you increase the order by 1. So at some point you will pass the capital N, the depth, and so at some point those relations will be useless, will not be useful. So there are only a finite number of Lie brackets that you care about. Okay, and of course, if you have a vector field and you multiply it by a smooth function, then it should also have the same order. So the correct way to do it is to consider those as modules. So that's the correct way to write the setting. You take di to be C infinity modules generated by vector fields of order I, and so what we have is this filtration. D0 is 0. I will never declare something to be of order 0. I wish I could, but I don't. I don't know how to conceptually do it. D1 and then D2 and so on. And of course, by everything is of order n, we mean this. And the point from the previous slide is that if you choose some vector fields, you can easily force this setting. And the relation is that this. Okay. So the point here is that the work, one of the works which appeared in the 80s generalizing this calculus, which to my knowledge is the most general in this direction, does this calculus, but when the di's are vector bundles. And he supposes this condition, but with di's sections of vector bundles of the tangent bundle. But in this case, this condition is a non-trivial condition, because you cannot force it. You need linear independence between vector fields and the Lie brackets and the iterated Lie brackets. So this is the difference between our work and the Mellins' work, what's called Mellins' calculus, where he supposes that those are vector bundles, in which case this is a non-trivial condition. In our case, that's, you can always force it, you don't care. Okay, and of course, those are finitely generated. It's important that, so as I said, we can work with locally finitely generated, but in this talk, you could just take finitely generated. That changes things. So now we want to define the inhomogeneous principle symbol. So we will equip the algebra of differential operators with a grading. And if we have a monomial, So if I have a differential operator, then I say that it's of order k if I can write it as sum of monomials of this form, where xi, so f is a function, so it's of order 0, xi is of order ai, so I take the sum, it's of order k. So it is what I wanted. I want the vector fields in di to be of order y, of order I. If I could write a differential operator as some sum of monomials of this form, I say that it's of order k. Okay, we'll see that the singularities, the fact that we left Mellon's situation and that vector fields are not linearly independent makes this relation not so simple. Some strange situation can happen. I put tilde just to clarify that it's not the usual order that we had from before. And clearly this is an algebra. And so as before, we could just take the same localized graded quotient, and that's a simple algebra. I mean, whatever principal symbol I will define, it has to be just this quotient. So the question is not what is the principal sequence, the principal symbol. The question is what is this algebra. So the first thing, it's not commutative in general. I could go back, and the reason is here in this equation. The commutator from the left-hand side is a priori has order k plus l, and on the right-hand side it also has order k plus l. What happened before in the classical pseudo-differential calculus was that this was of order 1. So this was a vector field which is of order 1, but the sum was of 2. So it was 1 less than it should be. Okay. So here, since I did not force that the Lie bracket becomes of order 1 less than it should be, the commutators, even at the level of the symbol algebra, this algebra, are not 0, at least in general. So I will explain how to obtain this algebra. It will turn out to be a quotient of a universal enveloping algebra. So I will define the Lie algebra, which gives you this quotient. So the Lie algebra is, you just take the same construction, but at the level of vector fields. So those are C-infinity modules. Of course, you can do this construction, graded localized quotient. So properties of this vector space, it's finite dimensional because each one of those modules is a finitely generated module. So when you take the quotient with Ix, they become finite dimensional vector space. Their dimension depends on x in a non-continuous way. So this is the biggest difference. This is the first time where a difference happens between our calculus and Mellon's calculus. If those di's were sections of vector bundles, then the dimension of this vector space will be the same as the dimension of the manifold. But here the dimension can be strictly bigger, and it can jump. I will give an example in 2 seconds. So that's the first thing. But the dimension, I won't write this later. So the dimensions are semi-continuous. That's not so hard to do. So at least we have this. It's naturally nilpotent Lie algebra, and the Lie bracket comes just from the Lie bracket of vector fields. Okay. You have a Lie bracket bilinear map, C-infinity of, not C-infinity, C bilinear map between from dk cross dl to dk plus l. When you localize, it actually becomes bilinear, which is well defined. That's a very nice, easy exercise to do. So you have a Lie bracket, and it's nilpotent because at some point you bypass n, and so this Lie algebra just keeps track of all of the relations that I discussed before, localized data point. And of course, we have a Lie algebra homomorphism, which goes from this space to this algebra, which just takes a vector field, sends it to itself as a differential operator. And so we have a map from the universal enveloping algebra to this algebra, this simple algebra. By construction, it's surjective because I mean, we forced it to be surjective. It's not injective in general. In Mellon's calculus, it's injective. In all of the situations I am aware of pseudo-differential calculus, in various situations, this type of maps always end up being injective. But in our situations, that's not the case. And we will see that the fact that this is not injective will play a very important role later on. And it could be and manifests itself in various forms. So here's an example. So you consider n to be 3, so the depth 3, and the manifold is R. I didn't write it, but the manifold is R. And you take the vector field. So I declare that this vector field x squared dx to be further 1, x dx to be further 2, and dx to be further 3. So everything to be further 3. So if x is not 0, the Lie algebra is R, because if x is not 0, everything just becomes of order 1 in a neighborhood of non-zero point. But at 0, you get R3. All of those elements become non-trivial in the quotients. So as you already see here, there is already a jump in dimension. And the Lie algebra is trivial. I could create another example where the Lie algebra is not trivial, but it's more complicated. This one is more simple. So here the Lie algebra is similar. So this is a commutative Lie algebra. So the universal enveloping is just polynomials. Now you consider this differential operator. So it's y squared minus x z. Y has order 2, so y squared has order 4. X has order 1. Z has order 3. So this is a nice operator which has order 4. But so as an element in the universal enveloping algebra, it's not 0. It's a non-zero polynomial. But if we can, but this is a differential operator on a manifold. I can actually compute it, and so I could. I mean, that's not hard computation. You could just compute the differential operator. You can find that it's actually equal to x dx. But that's the same as y. And I already declared that y has order 2. So this differential operator, even though it comes from an element in the universal enveloping algebra which has order 4 and non-zero, it's actually 0 because I take the graded quotient. So this is an element in the kernel. Okay. So the map is not injective. So we will study the kernel, and I will talk about the kernel later on. But for the moment, I will I mean, yeah. So you see, so I will take the Lie group, which simply connected Lie group, which integrates the Lie algebra. I mean, Mellon always in Mellon's calculus and in the classical pseudo-differential calculus, we always take the Lie group, which integrates this Lie algebra, and it's the same space as Gx, but the product is given by the Baker-Campbell-Hauser formula. Just like Gx is not, since Gx don't have continuous dimension, those things don't form a fiber bundle when x varies. Okay, so one can still define their C-star algebra, the C-star algebra of the bundle, but it's not a fiber bundle in the sense of topology. But you can still define their C-star algebra. I will give the construction in the end. Okay. Anyway, we take the set of irreducible unitary representations. And if I have a principal, if I have a representation which acts on a Hilbert space, then I could differentiate, take the differential of this representation. Now it acts on the universal enveloping algebra, of course, acting as a linear map on the smooth vectors. But of course, it doesn't pass to the quotient. So an ad hoc way of solving this issue is just to call those which pass through the quotient the algebraic characteristic set. It's a cheap definition, but it is what it is. I will give much better ways to understand this set later on. For now, that's it is what it is. So this set has the advantage that it's clear what the principal symbol is for a representation here. I could just So if I have a differential operator and I have a representation here, then this is well defined. I take the differential operator, put it in this thing, and by definition, d pi of d is well defined. And this is what we call the principal symbol at the point x and the representation pi. Okay. Now we go back to the inhomogeneous pseudo-differential calculus. So we define the principal symbol even before we define the inhomogeneous pseudo-differential calculus, but now we need to define those pseudo-differential operators. I won't give the definition here because it's technical. Any pseudo-differential calculus has usually quite technical definition, but I will explain the main idea. So recent work of de Boer and Scondalis and then and built on it by Van Herp and Juncken shows that if you want to define a pseudo-differential calculus, the only thing you need is a deformation group. So in the 80s, I think, Kohn gave a proof of the Atiyah-Singer index theorem using what he calls a tangent groupoid, which is a type of a deformation groupoid. And of course, in his work, it was clear that this has a connection with pseudo-differential calculus. But what the work of de Boer and Scondalis and Van Herp and Juncken shows is that you could actually go it in reverse, in the sense you could start with the groupoid, only the groupoid, and out of the groupoid you can build your calculus. And the advantage of this approach is that there are many properties of a pseudo-differential calculus that are annoying to prove and can be quite ugly. For example, usually a pseudo-differential calculus is defined in local coordinates. Then you have to show that it's invariant under local coordinates. You have to show that it's closed under composition, adjoint, so on. And the advantage of using groupoids is that all of those properties just disappear. They become simple statements about the groupoids. So it's a very robust method to define the pseudo-differential calculus. Of course, here in the work of de Boer and Scondalis and Van Herp and Juncken, it's applied to known pseudo-differential calculus, the classical pseudo-differential calculus in the case of de Boer and Scondalis, or the Mellins calculus in the case of Van Herp and Juncken. But what we will do here is that we will use it to define the inhomogeneous pseudo-differential calculus. So the groupoid that we want is this. This is the deformation groupoid. Cohn's tangent groupoid, here you have the tangent bundle instead of Gx. Okay, but this cannot be a Lie groupoid. The tangent groupoid is a Lie groupoid, but this cannot be because, as I said, this is not a fiber bundle. So the way we do it is that we define this groupoid as the holonomic groupoid of a singular foliation on M cross R. And then we are done. We know that holonomic groupoids exist, so we don't have to study them. So what is the singular foliation? Singular foliations have multiple inequivalent definitions in the literature. So I'm using the one which Andrew and Scondalis use, which is the most convenient for our purposes here. So a singular foliation in their terminology is just a locally finitely generated involutive module of vector fields. Involutive means closed under Lie brackets. On M cross R, you have a very natural singular foliation, which is this thing. So locally finitely generated, it's actually here, it's finitely generated because each one of those is finitely generated. Closed under Lie brackets, that's precisely the condition from before, that the bracket of CDI, of DI with DJ is inside DI plus J. So this is a singular foliation, that's direct to check. So it has a groupoid, and we show that its groupoid is, at least algebraically for now, is equal to this. Okay, so it agrees with what we think, what we hope. But the advantage of the holonomic groupoid is that it's not just an algebraic groupoid. It's covered by bisubmersions. Bisubmersions play the role of local charts for the singular foliation in the case of Andrew-Ladekis and Scondalis. In our case, those bisubmersions will exactly play the role of local charts for the pseudo-differential calculus. So I said before that we don't want to take local coordinates because the vector fields can have Lie brackets which are non-zero and which complicate situation. But bisubmersions is exactly what you should call local coordinates in this situation. Okay, and in fact, our operators are just standard oscillatory integrals on bisubmersions. But it should be remarked that bisubmersions are not subsets of the manifolds. They are lifts of the manifolds. They are manifolds which map by submersion to the manifold, by two submersions actually. That's what comes from. Okay. Now I define the algebraic characteristic set, which is it's a nice definition, but it's almost incalculable. And so now I will show that I will explain that actually it's not that awful, and you can actually compute it in some cases. So I will define two characteristic sets. So before I define them, so before I said that the principal symbol has multiple, the classical principal symbol has multiple ways to be defined. In the inhomogeneous calculus, this is similar, and there are multiple ways to define the principal symbol. I give one way, which is algebraically, and which led to the algebraic characteristic set. The point is that other ways lead to other characteristic sets. And we'll see that actually those characteristic sets are not the same. Okay. So Androladakis and Skondalis, they defined the dual of a singular foliation. It's a locally compact topological space. If the foliation is regular, then it's just F star. So if F is a foliation, it's F star. But in general, it's just a locally compact topological space. If you want to calculate it, in the case of this singular foliation from before, it's a topological space. Which, as I said, it is this. Of course, its topology is not the disjoint union. Okay. Well, it turns out that this set is not dense in this topological space. It is what it is. And so we call its boundary in this set the topological characteristic set. This set, in contrast with the algebraic set, is very easy to compute. In all of the examples, so for example, the example I gave with x squared dx, x dx, and dx, or any examples that you could think of, this set is usually very, very easy to compute. I don't have an example where it even takes an effort to compute it. In contrast, the algebraic characteristic set, even in simple examples, that takes some effort to do with ideas and so on. And I'm not good in algebraic geometry, so it's torture for me. Anyway, another characteristic set is the analytic one. So this comes from the C-star algebra. Here I work with the reduced one, but you could also work with the maximal if you want. So the reduced Androladakis and Skondalis, in addition to defining the singular, the holonomic groupoid of a singular foliation, they also defined the C-star algebra. So in this case, we can look at the C-star algebra, and the foliation doesn't have any derivative in the direction of t. So it's a C0 of R C-star algebra, and it fits in this short exact sequence here because this comes from the fact that at t non-zero, the foliation is trivial. There's only one leaf. So the C-star algebra is the C-star algebra of the trivial foliation. And at zero, this is one way to define the C-star algebra of the bundle of the groups that I said from before. I said that it's not a fiber bundle in the topological sense, but you can still define its C-star algebra. That's one way to do it. You can also define it intrinsically without talking about singular foliations, if one wishes to. Now, this C-star algebra turns out not to be a continuous field. The C-star algebra of the tangent groupoid by Kohn is a continuous field. The C-star algebra of the deformation groupoid, when one deals with Mellin's calculus, is a continuous field. But here it's not a continuous field. And this is the same issue as before. So the map from the universal enveloping algebra to the simple algebra is not injective. It manifests itself in different ways. So, but there is a very easy way to fix this. Of course, it's continuous outside zero. The issue is at zero. So there is a very easy way to fix it. It's not a true fix, but let me cheat. So one way is just you look at this idea. Okay? And you take the quotient by this. Now, the quotient will not be a continuous field, but it will be semi-continuous in the sense that the norm, the limit supremum of the norm of AT is equal to the norm of A0, but the limit itself might not exist. So even if you take the quotient by this idea, it might not be continuous field, but it will be semi-continuous, which is good enough for our purposes. Okay, so it just I never found the terminology semi-continuous fitted anywhere in the literature. Usually people talk about is it continuous or not. Anyway, so you can take the quotient by this ideal. So that's the ideal that fixes your issues, but that ideal is also an ideal of it's concentrated at 0. So it's a closed set of representations. So it's concentrated at 0. So you can consider it as an ideal of the fiber at 0. And so it's a closed set of representations of the group. Okay. And so we call this set the analytic characteristic set. Then the question is, what is the relation between those three sets? So this is a relation. The analytic set is equal to the topological set, and they are strict subsets in general of the algebraic one. So just a remark, the topological set was a subset of the dual of the Lie algebra. This was a set of representations I'm using here in the equality Kirillof's orbit method to identify. So this theorem says that first, the topological characteristic set is invariant under the coadjoint action. And when you use Kirillof's orbit method to think of it as sets of representations, it's actually equal to the analytic characteristic set. And this is a strict inequality of the algebraic characteristic set. I have an example which is not complicated, but in the end I decided not to write it because I found it to be. It uses a function which is x over the square root of x squared plus y squared with e power minus 1 over x squared plus y squared. So it's one of those flat functions which are awful. It doesn't help much with understanding what happens here. It's not very useful. But what should be, I mean, I hoped at first when we started looking at those sets, I hoped that the three would be equal. But yeah, they turn out not to be equal. But the example uses vector fields whose coefficients are flat functions, awful flat functions. It probably is true that if the vector fields have polynomial coefficients, one could prove that those three sets are equal. And in general, one could probably prove that this set is the algebraic closure of this set. The issue here is that those two sets are closed in the Euclidean topology by definition, but this set is also is closed in the Zariski topology. And the example is precisely because those sets in general are not closed in the Zariski topology. They can contain a non-trivial open set, yet at the same time not be the whole space. So it's probably true that this set is equal to the algebraic closure of this, but at the moment I don't have any idea how to prove this. It's probably not hard, but I don't know how to prove it. Anyway, it's not even important. I won't use this set. So now we go to the original goal of the talk, which is to prove that operators are hypoelliptic. So take a differential operator, then we say that it satisfies the Rockland condition if for any point in the manifold, for any representation in the analytic set, which is not trivial, this representation is invertible as a linear map on the infinity vector. So there's many things to be said here. So the first thing is, when we say a representation which is not trivial, this mimics the case from the classical pseudo-differential calculus, where we said that it's not zero if xi is non-zero. Okay, here where we looked at the cotangent bundle as a set of representations of the tangent bundle. So that explains this condition. Of course, since those things act on infinite dimensional Hilbert spaces, non-zero is not the correct thing to consider, and invertibility is the correct thing to consider. Okay. But it should be remarked, invertibility here is not the one, it's injective and have dense image. It's not usually subjective, so it's not invertible. Yeah. The last thing is that the correct one to use is the analytic one. Neither is the topological, neither the algebraic. The one that you should look at is the analytic one, because the statement at the end is a statement about C-star algebras. So morally it is. And so the only thing that you should really look at is the analytic set. In fact, and so the theorem that we prove is that if this satisfies this condition, then it's hyperelliptic. And you could prove this set without knowing what the analytic set is. Without knowing what the analytic set looks like, you can proceed and prove this theorem by functional calculus. And there is an article which proves some very nice result about operators which satisfy this thing, and we use his we use the authors. I forgot the name now of the author. I will find it once we finish. And we use his method to construct to prove this theorem. We adapt it in our case, and the main point is that we use the analytic characteristic set. The point of this theorem is that the analytic characteristic set is not so easy to compute from the definition, and so this theorem lets you compute it. As I said, the topological characteristic set is very easy to compute. The analytic one is almost impossible to compute, and the algebraic one is usually not so hard, but yeah, it requires algebraic geometry. So I will end with just an example explaining how those things work. It's a very simple example, but just to clarify how one actually proceeds to prove that something like this, that a specific differential operator on hand is hyperelliptic. So you can take this example, which appeared in the first slide. You take n to be 2. You could take it more. It will not change. It just makes the computations slightly, not even just a little bit more complicated. But you cannot take it less. That's the point. You need at least 2 iterated brackets to prove. So you take n to be 2. You take x to be the derivative with respect to x, and y to be x dy. And you take those to be of order 1 and dy to be of order 2. You calculate the Lie algebra, and you find that it's R2 in x is non-zero, and it's 3-dimensional if x is 0. And this is crucial. This differential operator is only hyperelliptic because it comes from a Heisenberg group. If I always obtain something which has the same dimension as the manifold, then I will always obtain something which is commutative. This is not good. So here it's actually good thing that it jumps in dimension. It's a feature, not about it lets us get groups which we cannot get them because of the dimension of the manifold. Anyway, the Lie algebra in this case is not commutative because the Lie bracket of x and y is set. Here, this is order 1, this is order 1, and this is order 2. Those are generators. So you get that this is the Heisenberg group. So it's this group, and x and y and z correspond to the x and y and z. Yeah. Okay. And the principal symbol, then you need to compute the principal symbol. So at non-zero points, this is a commutative group. So the principal symbol is just the Laplace operator. The same, this thing. And so at non-zero points, Rockland condition is clear. So the only thing that you have to verify is 0 points. So the representations of the Heisenberg group are very well known. They are either one-dimensional and they are parameterized by a plane, the commutative, the plane corresponding to x and y, or a one-parameter family with T and R star corresponding to the action of the representation on Z. It's a central element, so it has to be a one-dimensional representation. It has to be a linear. the product of a constant with the identity on any representation. So T. Anyway, so it's the Heisenberg group in L2, Heisenberg representation L2 form. In this case, the representation on the one-dimensional representation is still the same thing, and we still have that this is 0 if and only if xi and eta are 0, which is one-dimensional representation. But now we have to check the condition for the infinite dimensional representation. And in this case, H infinity Schwarz functions. You compute d by t, d by ty, and d by tz. You find that the principal symbol is this thing. So this is a constant. So you could divide by the absolute value of t. So you get here plus or minus the sign of t multiplied by lambda. So this you could renormalize, and then you could just consider this operator because that's the only thing that you have to consider. And this eigenvalues of this thing, that's the harmonic oscillator. You can even diagonalize it. It's well known in the eigenvectors. And the eigenvalues of this is a set of odd natural numbers. And so since you take plus or minus, lambda has to avoid the I times odd integers for the Rockland condition to be satisfied. And so you get the condition that we had before, that if lambda avoids this set, then the Rockland condition will hold, and then this theorem, then this operator is hyperelectric. Yeah. So thank you for your attention.
Okay. Thank you, Omar. And let's see if the audience, so we have some questions. Alain?
Yes, I got confused several times. I mean, so for instance, when you were taking this example with the three operator where you had x d by dx, you had x squared d by dx. I mean, this was a long time ago. I mean, yes, when you had somebody in the kernel of the map to the
yes. This here.
Yeah, this example, yes, exactly. So, I mean, none of these operators except for z is hypoelliptic. X d by dx is not hypoelliptic, of course. Because,
yes.
I mean, because the characteristic function of 0 infinity as the y of it is 0, but the function is not smooth at all. I mean, it has a discontinuity at 0. So
yes, but here the point of interest is not hypoellipticity of the vector fields.
I see. Yeah, it was that you had the kernel. Yes, I remember. Yes, yeah.
Yes, the point of interest is that there are some representations which I have to check Rockland condition at to ensure hypoellipticity.
Yes.
And those representations, one way to get them is using the kernel.
Mm-hmm. Yeah, yeah. Sure.
But as the example I said later on, that's strictly bigger than the set that you have to check on.
Yes, I see. I see.
But in this example, the three sets are equal.
Yeah, I see. No, and also I was also a little bit, I didn't follow very closely when you were saying that you assume that the principal symbol is invertible. You were acting on smooth vectors of the representation. And then you said, I think you said very quickly that it was not really invertibility, that it was injectivity and almost surjectivity. Or, I mean, so what is exactly the condition?
It's not surjective.
You don't assume it's surjective. I see. Okay. Okay.
No,
you don't assume it's surjective.
I mean, it cannot be surjective. I mean, if you.
Well, it depends. I mean, in your example with the Schwarz space, with the harmonic oscillator, it's an example
where Schwarz functions.
Yeah, but I mean, if you write Schwarz function in terms of the Hermite basis, then the operator is, I think it's invertible. I mean,
it's invertible if you look at its image as the H infinity. So that's what I wanted to.
Of course.
That's what I wanted to say.
That's what I have in mind.
That's what I wanted to say. It's not invertible in the sense of. I mean,
of Hilbert space, but it's invertible in the sense of H infinity. That's what I had in mind. Yeah. Okay.
Yeah. Okay. So that's what I wanted to say. It's not invertible in the sense of Hilbert space.
Okay. Thank you.
Yeah. Okay, Magnus, we have.
Thank you. I have a question concerning how it compares to.
Yeah, this is the article. Okay, I should not. Anyway, the name of the author, which I forgot to name, was this. Was Waldemar Heidisch. I'm sorry, I'm not very good with names, but that's the article which. And I should view. Yeah. So you had a question.
Yeah. Yes, Magnus had a question. Yes, you can.
Yeah, thank you. I was curious how this calculus compares with Mellon's calculus. If you have a say you have the specific situation of a codimension 1 subbundle. So this fits into Mellon's calculus. But say that this codimension 1 subbundle is also bracket generating. And then you take sort of these successive brackets to give you something, to give you these vector fields that you are looking at. How, I mean, the specific example I have in mind, if you have a boundary of a pseudo-convex domain, if it's only weakly pseudo-convex, but of finite type, then this is not going to be, and say it's not strictly pseudo-convex, then you don't have a contact manifold, but you still have a bracket generating distribution of vector fields.
We don't suppose any conditions of being a vector bundle. So only condition.
But say that it sort of fits into both Mellon's framework and yours. But you
Our
refine
framework
Mellon's.
is strictly more general than Mellon's framework. I don't really understand what you have in mind with our relation to Mellon's calculus. So I will try to explain. Our framework is strictly more general than Mellon's one. If you have a submodule, whatever it is, being of codimension 1 doesn't make much sense here. So if you have a submodule which is locally finitely generated and it's bracket generating, that's good enough for our purposes. You can use it. You can build a calculus in our context.
Yeah, but that's sort of my question. I mean, if you would use Mellon's calculus on this subbundle, you would get something.
So if it was a subbundle, you can use Mellon's calculus.
Yeah, but it would be something slightly different because it's not sort of bracket generating in the first step, but it's only bracket generating after several steps.
Yeah, but that's not an issue. You take n big enough.
Well, it would produce different results if you use Mellon's calculus of this as a codimension 1 thing if it's not bracket generating in the first step.
They will degenerate.
At some point, yeah, but it's sort of, in Mellon's calculus, you would sort of, I mean, you would have a very different Lie algebra in different points. I mean, in some points you would have a Heisenberg group if it's strictly pseudo-convex in that point. In some
yes,
points,
but here it will be similar. The group will not be the same group everywhere.
Yeah, but your GX would be different from the one constructed in Mellon's paper.
They will be exactly like the ones constructed by Mellon's calculus, if exactly the same as the one constructed by Mellon, if you take his example in our situation.
Yeah, but if you define the decay as coming from all the successive brackets, they will at some point reach all of the tangent bundle. But it's not necessarily happening in the first step.
Yes.
Right, so his Lie bracket will sort of be defined on, call this subbundle H, it will be defined on H direct sum Tm mod H, and at some point it will degenerate. It will sort of be a step 2 nilpotent Lie algebra.
Okay.
But if you include all the successive brackets, it will sort of have higher step length than 2.
Okay, so I will try to clarify. some confusion maybe. I don't know. First, you don't have to take them to be generated by the K-Lee brackets. Here, this is the setting. I can take them any modules. I don't care if they are generated by the K-Lee brackets or not. They have to contain Lie brackets of order K, maybe more, maybe less, I don't care. Okay. In Melon's case, he forces those modules to be in addition to those two conditions to be sections of bundles. So if you ever succeed in using Melon's calculus, you have to succeed in using our calculus. Okay?
Yes.
So the difference in our calculus is that I don't have to take X more than I should be in Melon's calculus, because the condition is vector bundles. If the vector bundles happen to be independent at some point, then not independent at another point, I have to add more to force them to be a vector bundle. We don't have to do this in our case.
Yeah, and my question concerns an example that would be able to fit into both situations, but differently. So if you have a bracket generating bundle, you can view this either as it's sort of the first step, and the next step is all of the tangent bundle. But you can also view it as you take these DIs of yours to be coming from all the successive commutators, and that will have a greater, I mean, it will have a larger depth than 2.
Okay, if you use the first one, you won't get something that's useful in your situation, because you essentially killed the fact that it's Lie bracket generating the group. So where is the group? Here, if you stop at n equal to 2,
yeah,
then you will get D1, the fiber of the module. If it's a vector space, it is vector, it's a fiber. But if it's a module that may or may not, it's the fiber, which might have bigger dimensions than the manifold. Okay, but you will get the fiber at 1, and then the next one will be just the tangent space quotient by the evaluation of the vector fields at that point. This group is always commutative. So if you do this, you are killing all of the information that you might be interested in. I already don't see a point. I mean, taking higher depths is always better. I don't see a situation where taking lower depths gives you a better. I mean, it might give you simpler computations, but I don't see a situation where the higher depths, some depths will work, but higher depths doesn't work.
Yeah. But I mean, the calculus will be different in a sense, right? So if you have, say, if
you use different modules, you get different calculus.
The reason I'm asking is it sort of for the Zeger projection. If it's a strictly pseudo-convex, it's in the Heisenberg calculus. But if it's weakly pseudo-convex, it's not clear.
Unfortunately, I don't know much about pseudo-convex domains. I don't know.
Okay.
I cannot answer.
Okay, thanks for the answer, and thanks for an interesting talk.
Okay, thank you. And are there any other questions or comments from the audience? Okay, Omar, maybe I have a last question for you. So it's a very naive question. At some point, you mentioned that in order to include the tangent groupoid construction in your framework, you consider something, consider singular foliation on M times M cross R, right?
Yes.
Is there any? Yes. Okay. Yes. So my question is, which so how exactly how the manifold M times are foliated? What are the leaves you consider?
The leaves for any t non-zero, there is one leaf,
Yes.
which is just M. And
Okay.
for any, and at t equals 0, the leaves are singletons.
Oh, okay, I see. Yes. Okay, thank you.
So I might mention this because I did mention it, but in our work we actually suppose that this is a regular foliation, in which case at t non-zero it's also fibered. This makes no difference. The only thing is that you replace compact operators with the system algebra of the foliation, but other than this, it makes absolutely no difference.
Okay.
If you want more complicated foliations at time non-zero,
okay, I see. Thank you. Okay, if there are no other questions, let's thank the speaker again for the interesting talk, and see you next week. We will have Rennie will speak.